Okay, while you're turning it in, we'll get started, okay? Okay, so here's where we left off last time. We said we built the compound interest formula for a certain number of compoundings every year. But then we said we could think of compounding every single moment, right? Every moment. And we need a new formula for that because then the value of n is like what here? So how many times are we compounding per year here? Like an infinite number of times. So there's mathematics to get from that previous compound interest formula to this one as n gets very, very, very large. We didn't cover that mathematics. But so here's the result though. So what does everything mean in this expression? What does everything mean in this expression? So we'll start with a of t. A of t would be what? A of t. Yeah, so it'd be the amount, the amount of the account or the amount of the investment or the loan after t years. T is years, right? That's our function notation. It represents output, right? Output. In this case, the output is the amount of the investment after t years. What is P?
The principal investment.
Principal. So initial investment, right? What is E?
A constant.
It's a number, right? E is a value that doesn't, it's like pi. It's a set value that is called the natural base. So in this situation where we have continuous compounding, this is the number that kind of emerges when you do the math to get this equation. E is the natural base. 2.718281828459045 da 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 da. Okay? What's R?
Rate.
Okay, so what kind of rate is that? This is the key. AP, yeah, it's as a decimal. It's a percent. It's a rate as a decimal. Is it APR or APY? APR. Is that the true percent increase per year? No. Okay. So in this formula, that R is the APR. It's not the true percent increase per year. To get the true percent increase per year, we think about combining that APR with continuous compounding. That results in some slightly larger, or it could be a lot larger, depends on the R, but a larger value of the true percent, and we call that what? That's the APY, okay? So again, R is the APR. It is not the true percent increase per time period T. Okay, and then T, of course, is time in years. Okay, so we call this thing R. We call it the continuous rate. Okay, so let me just warn you here. What we're about to do is, for some reason, the hardest thing all semester based on performance on the exams. So whatever you can do to zone in here, tune in, absorb this, watch the video a million times. But this next thing is like all these questions about this next part are always the lowest success of all the items all year long. Okay? So R is called the continuous rate. Is it the true rate of return? No. Okay? So it's not the true rate. So we give it this name, the continuous rate. Okay? So R is like an APR. Only when it's combined with continuous compounding is the actual percent known, and we call that APY. Okay, so what we can do now is we can kind of come full circle back to our original exponential growth formula, which was what? What was our general?
P times 1.
No. Just old school. Exponential growth. Just all exponential growth in general. Initial value times the x, okay? So this was our standard exponential growth formula. And you notice that's looking a lot like this continuous compounding formula. And in fact, we can now write that in this equivalent form, okay? So now we have two ways to write exponential growth in the original form, and now what we call in continuous form. In continuous form. K is called the continuous rate. Will K be the true rate of increase for 1 unit of X?
No.
No, because it's like APR. It's like that R value. Okay? It's the same conversation we had up there. So this K is called the continuous rate. It does not give the true percent change per unit of X. Are you hearing me?
Yes.
Okay, remember it. So, how do these line up? A is the same. What else is the same? The input is the same. So what does B, our growth, remember we said B was the centerpiece of exponential growth, right? We said B was the centerpiece. So now in this new form, what is B?
E to the K.
E to the K. Okay? So in this new form, B is equal to E to the K. So what is K? It's a rate. Is it the true rate of increase or decrease? No. What is B? Growth factor, not a rate. Does it reflect the true rate of increase or decrease? B. So from B, we can get the percent change, right? That's what we worked on last week. From B, we get the percent change. So here's how, given the continuous rate that doesn't give you the right percent change, you can get the right percent change by finding B. By finding B, then from B, we can get the actual percent change. Okay? B is the true growth factor for 1 unit of X. It reveals the true rate of increase. So K and B are like apples and oranges. K is a rate, B is a growth or decay factor. Okay? K is a rate, B is a growth and decay factor. But more than that, K does not give you the true percent change, whereas B corresponds to the true percent change. So from B, we can get the actual rate of increase, or I should have said or decrease here. Okay, anybody have a question? So we'll do some practice, but like I said, this from past evidence does not come easily. Please.
So E of K is the same as E of R?
Kind of, yeah. So E to K is now just in a general exponential growth, whereas E to the R is like specifically about continuous compounding. So this is the specific example of money. This is like the money version of this one. But this can be applied to now any exponential growth problem because it's basically the same as this. Okay? Okay. So suppose a nation's population has a 1-decade continuous rate of 19.2%. What's the true increase per decade and per year? So it's telling you the continuous rate is 19.2%. Of all the symbols on the page, what is it giving you? It's giving you K. So does this population increase 19.2% every decade? No, it does not. How do we find the true increase every decade?
E to the K.
Right, so this is our value of K. So this is K. He said 0.192. Right? So this has to be combined with the idea of continuous compounding to get the true percent increase per decade. And how will we find that number?
E to the K.
Yeah, we're going to find B, which is E to the K, which is E to the 0.192. Someone got a calculator?
1.21167.
0.2117. Is that right? So I rounded to 7. So what does this number mean? 1.2117, what does that number mean? That's the growth factor for what unit of time? 1 decade. And what does it reveal about how this population is growing? Increasing by? Okay? Compared with, so notice, it's kind of close to this, but when combined with continuous compounding, we know that compounding gives a higher rate if it's for increase, right? So 19.2% continuous is the same as a true percent increase of 21.17%. That's what's actually happening to the population. Please.
Is there a continuous decrease?
Sure. So yeah, we'll see some of those. Okay. So yeah, so you can have a continuous rate that's decreased, so that'd be a negative continuous rate. Okay. So now, how do you find the true percent increase per year? Find the true percent increase per year. So that's review. See if you can do it. Everyone should be able to do this. We got 21.17% per decade. How would you find how the population is changing per year? Actual. Okay, Derek, did you get it? How do we get from 1% change to another percent change? So we worked on that Friday. Britton, did you get it? I know Danny's got it. How about Josh? Joshua, did you get it?
Yeah, I got
Not the answer. Tell me how to do it.
I did 1.2117
1.2117 to the 1/10th, which gave you, what does that mean? What does that number mean?
That's the 1 year.
1 year growth factor. And what'd you get for that?
1.01939.
Okay.
And the percent would be 1.94.
Someone else get that? Okay. Is it the continuous rate for the decade divided by 10? No, it just coincidentally is close, okay? Coincidentally. You're not going to take a continuous rate for a decade divided by 10 to get the true percent per year. That's not. You've got to get, remember we said what's transferable? Growth or decay factor is transferable using exponents, right? So 1.2117 is the decade growth factor, so the 1 year growth factor is to the 1/10th. From the 1 year growth factor, we can get the true percent change per year. Okay, let's do this little task here at the bottom. So can you write a function? T decades, okay? So P of T, and write it 2 ways. Same function, write it 2 ways. Okay, Hamid, did you get it? Tell me one of them. Okay? How do you do? Like it? So that's one way to write it. So now we've got another way to write it that we just learned today. What's another way we can write this? Ashley?
230,168 times e to the 0.192 power n to the t.
How'd you do? Yeah, so both of these are the exact same function. They give the same ordered pairs of time and population. Okay, just two different forms. Right, this is our old school form, a, b to the t. Now this is what's called continuous form, because it has this continuous rate per decade. Which once again is not the true percent increase. True percent increase comes from the true growth factor over here, b. Questions on this slide? Remember it, okay? Watch the video, study, get it right on the exam. Last chance for questions. Okay, so we're going to move on to the next topic. Here's a kind of review question. For you to work on. Here, go for it. Okay, this is Sean right here. How'd you do on this? Tell me. It's the 1 day growth factor. He wants 1.45. Okay, what about the function then? Keep going.
F630 or f equals 630.
630, or the f of x equals 630 times 1.45 to the x. Okay, and then how would you find the number of bacteria after 10 days? Keep going, you're on a roll, Sean. Switch x to 10 at 10 days. That's exactly what the function does. Given any number of days, it tells us how many bacteria there is, right? After 5 days, it could tell us. After 2 days. Okay, so then when you see this, let's just go review back to the basics here. When you see this, what are you imagining, right? So it's not just this static formula that you're plugging into, but remember we emphasized that you really want to imagine something that's happening when you look at that formula. What is that about? Yeah, Adam.
There was originally 630 bacteria, and it grows by that growth factor, and it was 10 days.
Right. Okay. And so how does it do that? So exactly this, what are you imagining when you look at that right there?
45% increase for 10 days. And it grows by 45% like times
Okay, yeah, right, exactly. So on day 0, we had 630. How would we get how many we had on day 1? Multiply by 1.45. And so that would be how much you had on day 1, right? So on day 2, do it again. After 10 days, you will have multiplied by 1.45 how many times? 10 times, because every day you multiply by 1.45. So after 10 days, you will have multiplied by 1.45 10 times. But we don't want to write it that way. 1.45 multiplied together 10 times. That's r to the 10th. So you imagine every day it multiplies by 1.45. 10 means you just repeat that 10 times. Okay, make sure you have that kind of image of what exponential functions do, okay? So same setup, but now a different question. How many days will it take for the population to grow to 500,000 bacteria? How many days will it take for the population to grow to 500,000? So how would we set that up? Walden. No, I just want to set it up. Log, what's that? What's that? So, go ahead.
So you put 500,000.
Huh?
Equals, or I guess it would be, sorry, P equals 500,000 equals f of x equals 630 times 1.45 to the x.
Okay, so 500,000 is input or output?
500,000 is the
Output. Okay, so now 500,000 is the output, right? It's the output. And we're trying to find the corresponding input. How many days? Different question. Okay, so we start like this. 500,000 equals our output equals 630 times 1.45 to the x. We can divide, and we end up here. We get 793.65 equals 1.45 to the x. So the question is, what now? How do we get this number, x? There is some number of days that goes by such that the population reaches 500,000, but we've kind of got an algebraic roadblock here, okay? So what we say is, what we're really looking for is what we're looking for is the exponent of 1.45 that gives 793.65. Would you agree? Okay, so that's kind of the first step in solving this, is identifying what exponent it is. It's the exponent of 1.45 that gives or results in 793.65. Okay, so we have a more compact notation for that very thing. So this phrase, the exponent of 1.45 that gives 793.65, mathematically you have the shorthand notation log base 793.65, or log of 1.4 log base 1.45 of 793.65. Okay, so the purpose of a logarithm is to solve for an exponent. Maybe that's how you've thought about it in the past, and that's okay, that's true, but really we're saying something more kind of different than that, a little bit different than that. Really what we're saying is, what is that log? It's not to solve for an exponent. The log is the exponent. So this is what logs are, exponents. It's not about solving for an exponent. It kind of is, but more importantly, you see that when you look at a log, it is an exponent. Which exponent do we need here? We need the exponent of 1.45 that gives 793.65. And so that's the log base 1.45 of 793.65. So I'm guessing most of you probably haven't had this kind of perspective on it before, but this is a really helpful perspective. When you see a log, you think, oh, that's an exponent. And then these numbers tell you what exponent it is. So let's look at that. So in this case, that exponent turns out to be 17.97 days to get 500,000 bacteria. And we'll talk about getting that number later, okay? So we're going to practice this idea of logs first, but we'll get the numbers later, okay? So here we go. Logs are exponents. So these two statements are exactly the same. 1.45 to the x equals 793.65 is exactly the same as x equals log base 1.45 of 793.65. They both say the same thing. Both of those statements say this, that x is the exponent of 1.45 that gives 793.65. So how do they do it? So in the first one, you see x is right there. You see x is the exponent of 1.45. That gives that number. Okay, in the other one, it also says the same thing. It says x is, and then that whole thing means the exponent of 1.45 that gives that number. Okay? So again, the way we say that is the log base 1.45 of 793.65. Okay, so you're going to practice this. The way you practice is I'm going to give you a log, and the first thing you're always going to do is describe in words. This is step one. Always do this first. Describe in words which exponent it is. So if you've had experience with logs in the past, this is going to be new, and I want you to do it, okay? This is going to be really helpful. Try to adapt your thinking, maybe bring in this new perspective to what you've done before. If you've never done logs before, then that's better because you won't get tripped up by maybe something you've done before. So first you're going to describe what it actually is, and then you're going to write your description as a statement. Just based on what you say, you're going to write out the math. Okay, so here's what we do. So we'll do this one together. So if we were to describe in words exactly which exponent that is, what would we say? A is?
Base 5 that gives 25.
The exponent of 5 that gives 25. That's what this means. It means the exponent of 5 that gives 25. And so now based on that, if you have A is the exponent of 5 that gives 25, so what statement can you write? What can you write? If A is the exponent of 5 that gives 25, then you can write out a new mathematical statement, which is 5 to the A equals 25. And we all know what A is. 2. So since A is 2, then that's what the log base 5 of 25 is. Because it's the exponent of 5 that gives 25. Okay, your turn. Go. Do the statement first. Write out the statement in words. Based on the words, write out the math. So write out the words first. Based on the words, then write the math. Have you seen it this way before?
Not with the exact words,
Yeah.
but they did describe it.
Okay, in words. Nicholas, did you get it in words? In words, what is this? He said Z is the exponent of 2 that gives 16. Agree? Okay. And let's see, who else? Wesley. So if Z is the exponent of 2 that gives 16, then what mathematical statement could you write? So just think about exactly what that means. Z is the exponent of 2 that gives 16. So what would that be the same as? So how about just Z is the exponent of 2? So what would that represent? Z is the exponent of 2. 2 exponent z equals 16. Okay, and so can we figure out in your head what that is? 2 to the what is 16? 4. So that's what the log base 2 of 16 is. It's 4. Because it's the exponent of 2 that gives 16. Anybody have a question? More practice. Go. Write it out in words first. Then based on the words, write the math. Sarah, did you get it?
P is the exponent of 4 that gives 164.
P is the exponent of 4 that gives 164th. And that would mean what mathematically?
That 4 to the power is 164.
That's it. 4 to the pth power is 164th. So now that if we want to try to do this in our head, it helps to rewrite 164th as 1 over 4 cubed. And so then we can kind of see, maybe see what p is. What is p? -3, right? Rules of exponents, right? If an exponent is negative, that means there's a positive exponent in the denominator. So we've got this positive exponent in the denominator, which would be equivalent to -3 here. So the log base 4 of 164th is -3. Anybody have a question? Are these the ones you were doing? Okay, what about C? Let's look at C in number 4. Log base 3 of -2 equals k. What exponent are we talking about? Brandon? What exponent are we talking about there? What? This is what this phrase, this practice we're practicing over and over again. Eric? No. Yeah, k, sure. But what is it? What exponent is k? So we didn't practice all that for nothing. Let's see, way in the back there. Faisal. The exponent of 3 that gives -2. And so how could you set that up into an equation? So k is the exponent of 3 that gives -2. Therefore, nice and loud. Okay, well just so k is the exponent of 3. What does that mean? K is the exponent of 3. So what to the what? K is the exponent. K is the exponent. So what to the what? TJ. Yeah, that's it. K is the exponent of 3 that gives -2. What about K? So what about a value for K? Yeah. What's that? Okay, it doesn't exist. You can't raise something to an exponent and get a negative number. Even if you raise it to a negative, we know you get 1 over 3 to the positive. So no matter what you raise 3 to, you always get a positive value. So this is undefined. This log is undefined. when you raise any number to an exponent, or a positive number, when you raise a positive number to an exponent, doesn't matter what the exponent is, you get a positive number. So this is impossible. There's no exponent of 3 that gives -2. He said imaginary, so we have to be in a different number system.
What if they put what's it called a negative sign and like put decay in parentheses and then put a negative outside of it? Like
No, it doesn't matter. It doesn't matter what exponent you have. You raise 3 to any exponent, negative, 0, positive, big, small. You can't get a negative. You can't get a negative value. So 3 to the k looks like this. If this is k here, and your output is 3 to the k, your graph looks like this, which means that the output is always what? Always positive. You can't get an output of -2 if it's 3 to the k. Okay, in number 4, any by request. But do this, okay? Practice this. Because that's what logs are. They're exponents. So you should be able to look at a log and know exactly what exponent you're looking at. Here we're looking at, it's trying to tell us that we're looking at an exponent of 3 that gives -2. And you can just look, you can just read it left to right. You can just read it left to right. The exponent of 3 that gives -2. So even the notation just allows you to read it left to right. The exponent of 3 that gives -2. Sure. Okay, cool. Yeah, good example. So we need to, before we isolate we have to isolate the exponent. We can't really, in this form, we can't do it, so we need to do something first. What do we need to do? We need to get that exponent by itself. So log base 4 of 22 equals b over 3. Now we can talk about what exponent we've got. So somebody new. Get some more laziness involved. How about Margarita? So what does this mean? Log base 4 of 22.
That b divided by 3
Okay?
is the exponent of 4 that gives 22.
She said b divided by 3 is the exponent of 4 that gives 22. Agree? Nailed it. So what can we say mathematically then?
4 and then b divided by 3 equals 22.
So now most of them you can't solve in your head, right? So 4 to the what equals 22? Well, something between 2 and 3, right? Because 4 squared is 16. 4 cubed is 64. So something, b over 3 is something a little bit greater than 2, right? Because 4 squared is 16, but we have a 22 now. So we can make a guess and say b over 3 is 2.1 or 2.2 or something like that. As a guess, okay? All right, then going back. So I'm not going to do that. So I want to show you one more thing here. There are 2 special logs, okay? What's the value of that? I heard 2. I heard 100.
3.
I heard 3. What do you do first? What do you do first? Just humor me. Just, what's that? What do you do first?
You write it out in words.
Or just say it in words. What is it?
Uh,
You just read it for left to right. We got to get fast at this. Just left to right. Log is what? A log is a exponent. So you can just read from left to right. The exponent, 10. You got to get faster at this. So the exponent of 10 that gives 1,000. So what exponent of 10 would give me 1,000? 3. Because our number system is based on 10, we can also write this log with nothing there. When nothing is there, it means base 10 because our number system is in base 10. So when you just see log and no base, imagine a 10 there. It means 10. Okay, we got another one. So this is called the common log. Okay, we got another one. Tell me what you're looking at there. What is it? The log of e that equals 5. The exponent of e that equals 5. And so let's name it something. We'll name it x. So tell me what it is, Benji. E to the x equals 5. Okay, remember E was our special base for continuous growth or continuous decay. So that's a special one too. And that's called the natural log. So that can be written as ln. So when you see ln, ln means the same thing as log base E. These are equivalent. Log base E is ln. So what are ln's? They're exponents of E. The natural log of something, it's an exponent of e, because log base e, right? So whenever you have an ln, you think, oh, that's the exponent of e that gives me, in this case, 5. Okay.